Rutherford's nuclear model of atom. Let's understand Rutherford's nuclear model of atom. In this experiment, fast-moving alpha particles were made to fall on a thin gold foil. Alpha particles are doubly charged helium ions. Since they have a mass of 4 units, the fast-moving particles have a considerable amount of energy. Alpha particles emitted by a radioactive source were collimated into a narrow beam by their passage through lead bricks. The beam was allowed to fall on a thin foil of gold. The scattered alpha particles were observed through a rotatable detector consisting of zinc sulfide screen and a microscope. The scattered alpha particles, on striking the screen, produced brief light flashes. These flashes may be viewed through a microscope, and the distribution of the number of scattered particles may be studied as a function of angle of scattering. The alpha particle scattering experiment gave totally unexpected result. The following observations were made. Most of the fast-moving alpha particles passed straight through the gold foil. Some of the alpha particles were deflected by the foil by small angles. Surprisingly, 1 out of every 12,000 particles appeared to rebound. In the words of Rutherford, this result was almost as incredible as if you fire a 15-inch shell at a piece of tissue paper and it comes back and hits you. Many of the alpha particles pass through the foil. It means that they do not suffer any collisions. Only about 0.14% of the incident alpha particles scatter by more than 1 degree and about 1 in 8,000 deflect by more than 90 degree. Rutherford argued that to deflect the alpha particle backwards, it must experience a large repulsive force. This force could be provided if the greater part of the mass of the atom and its positive charge were concentrated tightly at its center. As you can see, there is a large difference between the expected and the observed results. Rutherford said that for the alpha particle to go backwards, a large repulsive force should act. This force may be possible due to a central part of the atom having large mass and positive charge. The magnitude of the force of repulsion between the alpha particle and the positively charged nucleus can be determined by F equals to 1 by 4 pi epsilon naught multiplied by 2e into Ze by r square. Here r distance between the alpha particle and nucleus. Ze charge on the nucleus. 2e charge on the alpha particle. F force between the alpha particle and the nucleus. The magnitude and the direction of the force keeps varying as the alpha particle approaches. Let's understand alpha particle trajectory. The trajectory traced by an alpha particle depends on the impact parameter b of collision. The impact parameter is the perpendicular distance of the initial velocity vector of the alpha particle from the center of the nucleus. The impact parameter is the perpendicular distance of the initial velocity vector of the alpha particle from the center of the nucleus. Large impact parameter, less deflection, almost 0 degrees. Small impact parameter, therefore large deflection, almost 180 degrees. Since the positively charged alpha particles get deflected, hence the nucleus should contain positively charged.